You ever just stop and think about a single raindrop? I mean, it falls from thousands of feet up in the sky, but when it hits you, it's just a gentle tap. Well, there's some absolutely incredible physics hiding in that journey. Today, we're going to pull back the curtain on the secret that keeps a gentle rain from being, well, a full-on barrage of tiny bullets.
It's a great question, isn't it? Seriously, if you drop something from that high up, you'd expect it to get going incredibly fast. So why don't we all need to carry around steel umbrellas? The answer lies in a really elegant piece of physics, a concept we can actually watch in slow motion using, of all things, a simple jar of honey.
So, let's set the scene. Our whole story really kicks off with a simple observation, a mystery that anyone who's ever watched a storm has probably wondered about.
And that's the heart of the puzzle right there. We all know raindrops speed up because of gravity, right? But it seems like they only speed up to a certain point. It feels like something is kind of putting on the brakes. Understanding this invisible braking force is the key to everything.
To solve this rainy day mystery, we need to see these forces in action. And to do that, we're going to slow things way down with a simple and kind of sticky experiment. Let's talk about the honey jar.
The setup here is just beautiful in its simplicity. We've got a very thick, or what scientists call a viscous fluid. That's our honey. And then we have two objects of different sizes. This little experiment is going to let us see the forces we're talking about in super slow motion. Okay, so when we drop them in, something fascinating happens. Yeah, both balls speed up at first, but then they both seem to hit a ceiling. They just stop accelerating. They settle into a final, constant speed. And look, the bigger ball gets to a faster constant speed, but it still has a limit. This idea of a final, limited speed, a physical speed limit, that's the secret we're trying to unlock.
So what in the world is that invisible force? What's putting the brakes on those steel balls in the honey? Well, the answer has a name, and it's called the science of drag.
This right here is the hero of our story. As any object moves through a fluid, doesn't matter if it's thick honey or even thin air, the fluid itself pushes back, resisting that motion. Think about trying to run through a swimming pool. The water pushes against you, right? That pushing back force, that's viscous drag. Now, this whole pushing back thing wasn't just a vague idea. Back in the 19th century, a truly brilliant physicist and mathematician named George Gabriel Stokes basically cracked the code. He didn't just describe the force, he gave us a precise formula to calculate it.
And here it is, his elegant solution, Stokes Law. Now I know, it might look a little intimidating with all the symbols, but trust me, every single part of this formula tells a piece of our honey jar story. Let's break it down.
So what are we really looking at here? F is that drag force we're trying to figure out. That Greek letter 8S stands for the fluid's viscosity, its thickness, so honey has a way higher viscosity than air. R is just the radius or the size of our object, like our little steel balls, and V, well, that's its velocity, how fast it's going.
So here's the crucial takeaway. The drag force isn't some constant number. It gets stronger if the fluid is thicker, or if the object is bigger, or, and this is the absolute key to our whole mystery, if the object is moving faster. The faster you go, the harder that fluid pushes back on you.
And this brings us right to the climax of the story. We've got these two forces going at it, gravity pulling everything down and this drag force pushing everything up. So, what happens when they finally meet?
I want you to picture it like a tug of war. On one side, you have the pull of gravity on our falling object. That force is constant. It doesn't change. But on the other side, you have the drag force. It starts at zero, and it grows stronger and stronger and stronger as the object speeds up. Sooner or later, something's got to give.
Let's just walk through it. First, you drop the object. Gravity grabs it, and it starts to accelerate. As its speed picks up, that viscous drag force gets bigger and bigger. And then you hit this magic moment where the upward push of drag becomes exactly equal to the downward pull of gravity. The forces are perfectly balanced, and at that exact moment, acceleration just stops, dead in its tracks.
And that final, constant speed, it has a name. It's called terminal velocity. It is the absolute maximum speed an object can reach when it's falling through a fluid. It's literally the speed limit imposed by the laws of physics. Okay, time for the big payoff. Let's see Stokes' law in action. We've gone from a rainy day to a honey jar to a physics formula. Now, let's put it all together and finally solve our original puzzle.
And there you have it. Air, as thin and empty as it feels to us, is a fluid. As a raindrop falls and speeds up, the drag force from the air pushes back harder and harder until it perfectly balances the force of gravity. The raindrop hits its terminal velocity, a speed that's, pretty fast, but thankfully not bullet fast.
And believe me, this idea goes so far beyond just the weather. Understanding Stokes' law is absolutely crucial in tons of different fields. It helps meteorologists model how clouds form, it helps engineers design the perfect paint that doesn't drip, it helps doctors understand blood flow, and it's used to separate tiny particles in industrial processes. This one simple idea has applications that are just incredibly wide-ranging.
So if you need the one line, cram for the exam takeaway, this is it. Stokes' law is the key that unlocks the whole relationship between a fluid, an object, and the forces that control how they move. It's the simple, elegant reason a gentle rain is even possible.
It really makes you wonder, though, doesn't it? We just saw how a hidden force of physics turns what could be a dangerous projectile into a gentle raindrop. So what other invisible rules are out there, quietly and elegantly shaping the world all around us, just waiting for us to notice them?